All right. Good morning. I posted homework 2 last night. Homework 2 is due next Monday, so you have just under a week to finish this. It is mainly covering all the things that we talked about last week. I will also publish homework 3 very shortly. Homework 3 will be the final homework that is due before the midterm. Homework 3 will be due not next week, but the week after on Monday, and then the midterm will be on Wednesday after that. So 2 weeks from today's midterm. Yeah. And then that Friday is canceled. I assume maybe people are traveling for Halloween, so I just canceled that class after Halloween. Yeah. Okay, homework 2, I want to quickly just scroll through it. So first question is doing some Boolean algebra simplification. I'll post like a cheat sheet, like summary from CSE100 just so that we're all on the same page on this. It's just kind of important to stay up to date on this, so I just threw in a simple question. Then I have this basic transmission gate circuit. So hopefully we all remember transmission gates from when I covered it in lecture. And you're welcome to go back and watch that lecture to remind yourself exactly how to tell if you have strong current flowing through or weak current flowing through. Let me know if you have any questions on this at some point. Question 3 is turning a mux into a gate. So turning it into an and 2 gate, into a not gate, and into an or gate. So I'm assuming that, I think we've done all of these in class already, so it's kind of just review to make sure that your notes are in order. Question 4 is converting between Verilog and schematics. So for question 1, you're given this schematic. You're asked to write Verilog that implements this schematic. And then down here, you are provided Verilog and asked to draw the resulting schematic. And you are allowed to use digital JS to kind of help you, but you have to be the one to actually draw out the circuit. You can't just screenshot digital JS straight out. Yeah, okay. And then the next 2 questions are just kind of basic, like here's a circuit, and then what is the waveform? So here's this question that has a couple flip-flops, OR gate, AND gate, another OR gate. And then similarly down here now there's an XOR gate and there's another OR gate. So yeah, so that is the entire homework. So it is due next Monday. So yes, please start working on this as soon as possible because yes, homework 3 will be due the week after that. And so all of this will be really good preparation for your for your midterm, which is in 2 weeks. Yes. And I have not yet posted solutions for homework 1. I was going to yesterday, but then I ran out of time. I will post them today. And yes, and then hopefully homework 1 scores will be released sometime next week. I'm expecting about like a week and a half delay between when you submit the homework and then you get your grade back. Okay. Any questions on this? Okay. Okay, good. So you all started your lab yesterday as well. I was looking and I walked into the lab a couple times. It seems like people are doing very well, getting things started, writing Verilog. We're gonna just go over more flip-flops for today and all throughout next week. It's just this unit is gonna be all on flip-flops. So if you were a little bit lost on lab yesterday, hopefully you'll be more prepared for lab tomorrow. So here I have the lab pulled up. So here's the assignment. Okay, and the first question that you were asked, so there's a pre-lab attached with 2 questions. So the first question is saying draw a circuit schematic that implements this expression. But particularly, it shows how to do constant multiplication. So I figured probably beneficial to go over some of this. Did anyone figure out how to draw this out? Did anyone draw out the circuit? Yeah? Did anyone read this part? No?
I didn't see that on here.
What was that? It's not, it's not in it?
No. we see that?
In the one that we downloaded, that question was not there.
Oh no, what a catastrophe. Wait, really?
Yeah.
Wait, okay, that's not good. I may have accidentally uploaded last quarter's lab or something. This lab is slightly different. So not totally, yeah.
It says the due date on the one that's uploaded says it's sometime in July.
Okay,
Oh, yeah.
well, sorry about that. Okay, I will correct that. The lab, any progress that you made is going to go, it'll still work. The only things I changed for this lab were clarifications, and then I added a couple pre-lab questions. Sorry about that. I don't know how that mix-up happened. Sorry about that. Okay, I will fix that. Thank you for letting me know. Yeah, so this lab is due October 24th. Okay, I'll do that. Cool, okay, well, if I had released the correct lab, then you would have seen this question. And this question says, so here's this expression, and this expression will let you convert from a coordinate, so like an XY coordinate, into an address into your big image ROM. Because remember, so your image ROM is, you can think of it kind of like a lookup table, except the lookup table that we used for last lab was a lot smaller. So it had 256 entries. But this table, do you remember how big this table is? Anyone know? I actually don't remember the exact numbers, but it's something like, and it's not, all right, my computer is super laggy for some reason. It's so sad. Come on. Weird. Okay. Well, it's quite large. I think it's like it has like 1,000 entries or more than that, like a few thousand entries. So this table is much larger than what we used for Lab 2. So therefore, we actually need to use slightly different hardware. Or I guess I gave you the starter code, so it all works already. But this lab, instead of using just a lookup table, now we are using an actual RAM that is on the FPGA. So the FPGA, so it has lookup tables, it has muxes, it has flip-flops, but it also has internal RAMs. What is a RAM? Does anyone know? Yeah.
Random access memory?
Yeah, random access memory, meaning, so it's a memory that you can feed in any random address and you will get back the data that's stored at that address. And RAMs can be quite large. I think the RAMs that are inside of this FPGA, actually I don't remember, but there's something like, whatever, they can have 36,000 elements or something. Like these are very large blocks of data, much larger than, just like typical lookup tables that maybe only have like, I don't know, 64 elements or something. RAMs can have 36,000 elements. But do we remember, I'm not sure how clear it was in the lab that I gave you, but do we remember what the main difference is between the RAMs that you were using in lab 3 versus the lookup table like RAM that you were using in lab 2? What is like the main difference as like a user perspective? Like what's the difference between like your Verilog implementations? Yeah. Remember? Yeah. Yeah?
Maybe you can get a clock.
Exactly, yeah, exactly. So when you have a very large RAM, it helps to actually have a clock signal in it, and it's for kind of like analog reasons. I won't go into the actual circuit schematic of how to implement a memory, but there's like cool kind of amplifiers and things that operate with a clock, and so therefore your large RAMs require a clock, and therefore that means that when you try to read out data, does it happen instantly, or how long does it take when you try to read out data from a large RAM? Yeah. No? Yeah. How long does it take to read out data from a large RAM? Yeah.
Every time the clock goes high.
Exactly, yeah, it takes one clock cycle. Yeah, so keep that in mind. So the large RAM that we are using for lab 3 that was already given to you, it's in the images module, that RAM takes one full clock cycle in order to actually read out its data. That's very different from the lookup tables that we've been used to. Yeah. Yes, and so this lab, I wanted to also show you. So I can open up the, not this file. So I wanted to quickly open up the make file just to show you kind of what's inside. Have people worked with make files before? Yeah, yeah, a little bit, sure. So I guess I went over them a little bit already, but I'll just remind you one more time. So this first kind of word here that precedes this colon, do you remember what this is called in a make file? Yeah, this is a target. So I've declared a bunch of targets here. I have a target here, I have a target, whatever, target here. And a target means that I can type the command make, and then I can enter whatever the target name is. And so if I wanted to maybe generate the bit stream, I could pull up this target right here. So this target of whatever, synth, basis 3, build, basis 3, whatever. I can take this entire file, which is actually just the bit stream that was generated, and I can just copy this, and now I can type in make, and then now it will run the bit stream. What's the benefit of generating the bit stream directly versus just running Vivado program? Why would that be beneficial? Yeah?
Might be faster.
Yeah, it's a little bit faster because with make Vivado program, after it generates the bit stream, then it tries to program the board, but I don't have a board attached. So if you ever want to just like generate the bit stream, but you don't want to immediately launch another Vivado instance to program your board, you can just go and select this bit stream target and then make that. So it's currently making it. It'll take a little bit to run this, but I want to open up Vivado once this finishes, and I'll show you something kind of fun. Yeah, that will link back to what we talked about yesterday. Okay. So, but first I wanted to talk about VGA. So this lab is getting VGA working. VGA is such an incredible protocol. It's a video protocol. And what are other video protocols that we're used to? Anyone shout one out? DisplayPort, yeah, what's another one? HDMI, something else? Composite, component, DVI, yeah, and there's others. Yeah, so there's a bunch of different protocols for, like, if you have like a wire and you're like, how do I send video through this wire so that like I can plug in like my TV into my computer or something. There's a lot of different protocols. VGA is the best one for hobbyists because I'm assuming that you all kind of read through the explanation of VGA, and it wasn't too tricky to probably understand. So the way that VGA was designed is it was designed with CRTs in mind. So CRTs, cathode ray tube screen. So it's if you remember like the big box TVs or big box monitors, what it actually would have is it would have an electron gun at the back of it, and the way that it would light up the screen is there would be this phosphor layer on the screen. The electron gun would sweep across the screen, and it would go like line by line, and it would shoot electrons at whatever pixel it wanted to light up. And if it wanted like a black pixel, the electron gun just wouldn't fire at all. If it wanted a fully white pixel, then it would fire at both like the red, green, and blue phosphors on the screen. And it would go and all the way and light up all the phosphors that it needed for that line. Then after that, then it would swing back around and then now do the next line. And after that, it would swing back and do the next line, and swing back and do the next line. And then finally, after it had done all of the lines, then it would swing back up to the top and then start over again. And in the way that it would know, this is how the CRT TVs would work, but once it reached the end of a line, or once it reached the end of the screen, it needed some circuitry to know when to reset back to the start, like reset back to the next line or reset back to the next frame. What signal is required for this? Do you remember? Yeah, the sync pulse, right. So yeah, there's a horizontal sync pulse and a vertical sync pulse. So the vertical sync pulse, the idea is like as it scans across the screen, once it finally reaches the end of the screen, the sync pulse is what denotes like, hey, okay, it's time to switch, like bring the electron gun back to the front. And then this sync pulse will now go back up high, so it'll disable. Okay, so side comment. If H sync and V sync cause the electron gun to like go like to activate like back to the front when the pulse is low, then do you remember what that was called? What is it called when the signal, when it's low, it like activates the thing? Yeah, active low. Yeah. So anyways, so therefore we can say that V-sync and H-sync are active low because they're high most of the time until they need to go active, then they become low. Yeah. Anyways, okay, active low. Cool. Okay, so now it's working. So it sends one line. Then we reach the end of the line. Sync pulse goes low, swings back. Sync pulse goes high. Then it starts going again. Okay, sync pulse goes low, swings back. Sync pulse goes high, and we'll do this all the way until it reaches the end of the screen. Then finally, now a different wire, the V-sync pulse, now will go low, okay? And now it'll swing all the way back up, and then V-sync pulse goes high, and then now it goes back to drawing the next frame. Yeah. So that is how CRTs work. And I actually have pulled up, so I have a simulation, so I ran MakeSim. I'm not going to run it again because it takes kind of a while, but I recently just ran MakeSim. And then after I ran MakeSim, you can run GTK-Wave and then dump.fst. Okay, what is GTK-Wave used for again? It's for viewing the waveforms. So if you think back to homework 2, right? So we would call this a waveform diagram, where we're asking you to fill in all of the waves. Like basically, it's like the oscilloscope traces. So it's like voltage over time. Yeah. So if I can now see every single signal in my entire design, GTK wave, and dump.fst. FST stands for fast because it's a like faster way of storing waveforms than the most previous version before FST, which is kind of a funny name. It's like they made a really slow thing, and they're like, hey, let's make a faster thing, so they called it .fast. But then fast is kind of outdated now, so now there's more up-to-date things, but we don't call it like FST2 or something, we call it other things. Anyways, it's kind of funny. Maybe not the best idea. It's like if you make something like faster, to just call it fast, because eventually technology will like improve, and it's like, so FST isn't even the fastest thing anymore. Anyways, fun stuff. That's what FST means. It means faster than the previous version that stored waveforms. Okay, so then we can open this now. Okay, has anyone kind of opened this already and looked at this? Okay, so like maybe a third of the class. So inside this, we can see the hierarchy of all of our signals. So what does TB stand for? Does anyone know? Test bench, yeah. So TB stands for test bench. So this is code that I wrote myself. We can look at it. So it is in DV. Okay. What does DV stand for? Design verification, exactly. Yeah, lots of acronyms in chip design. Okay, so in DV, we can now open the TB, the test bench. And so here we see, so it's slightly different from the lab that I already provided you, but I'll update the test bench. My apologies. So you can see that here I'm setting a clock signal. And so the clock signal, you can see, so I'm initially setting this wire to 0, and then I have this like basically while loop, it's a forever loop, that will just oscillate the clock. So it'll say clock is equal to not clock. Then it will send a delay. It'll have a delay of whatever this delay, which will exactly equate to 25.175 megahertz, which is just required for the slab. And then after it does that delay, then it'll run it again, then run the delay, then invert it again, run the delay, invert it again. So that's how the clock is created. If you ever wanted to make your own test bench, this is how you create a clock. And then, yeah, and I'll kind of skip ahead a little bit. So here is where I create the screensaver top module. You can notice I'm actually missing a few ports. What ports am I missing from this? Yeah, I'm missing like all the sync pulses. I'm missing probably the colors as well. I'm actually missing all those, but specifically I'm missing all of the outputs, because you actually technically don't need to assign all outputs when you create a Verilog module. You can actually just do, where is it? Yeah, you can actually use something called a hierarchical reference. So I have screensaver dot, and then I can just grab the output like this. Yeah, this is only for test benches, so you can't do this in your code. So maybe it's not good that I'm showing you this, but yeah. So in case you were just trying to understand what is inside the test bench, this this is just a quick explanation of it. So yeah, please don't use hierarchical references in your code. Your code won't work, and you'll be sad. So okay, good. So we can see here what is happening is, so we wait for the first vsync. And then after that, then we request a different image from the screen. And then after that, then we wait for another vsync. And it looks like we wait for vsyncs until we finally reached the correct number of frames. So if you did not implement vsync at all, let's say vsync was held high for the entire time, then what would end up happening right here? So if you didn't implement vsync and you just held it like at 1 the whole time, or held it at 0 the whole time, what would end up happening right here?
Would it never go down to the next line?
Yeah, exactly, right? So it would never, it would stall. It would just wait here forever. It would always wait for the pause edge. You would just wait. And then you would get an error. What error would you end up getting? You would get, so I think down here, where is it? Yeah, hold on. Oh, do I not have? Wait, I thought I said a timeout. I passed it? So I'm looking for the timeout. So I believe I've made a timeout functionality. Wait, oh, here it is. Oh, good, okay. Yeah, so what you would have is you will get this error, which says timed out. So I just have this quick check right here that's just waiting a very long time. So it's just making sure that your simulation doesn't go on for too long. Otherwise, it would just go on forever. So yeah, so I just have this little timeout check right here. So if you ever see this, it probably means that your either vsync or hsync aren't working properly. But what you can do is you can go into your GTK wave, and you can open up the test bench, and then you can open up screensaver, and you can see all of the different signals that are inside this. And if I want, I can pull up sync, and let's do sync O, sure. So this is vsync, that's hsync, and you can see it's 0 right now, and if I try to scroll along, then it's like, oh, what's going on? But I can zoom out with these buttons up here. So I can click zoom out. It takes a while to zoom out, but there we go. Okay, we're getting signals. Let's also add the clock, because that would probably be helpful. Okay, so there's the clock. So you can see the clock is happening really quickly, but I can keep zooming out. And okay, so here we can see all these little pulses to low right here from the hsync. What do each of these pulses represent? Yeah?
We're reaching the end of like a horizontal line.
Exactly, yeah. So when we reach the end of the horizontal line, then now the electron gun will sweep back to the front. Yes, okay. And now we can keep zooming out and keep zooming out. And then now we see these little blips here. And these are from the vsync. And what do these represent? Yeah, and end of the frame, end of the screen. Yeah, cool. Yeah, so I think that this is such a great visual way of really seeing how vsync works. It's just one of the coolest protocols, in my opinion. It's a very common hobby project of people trying to get into FPGAs for the first time, or getting into chip development. Because unfortunately, you can't really do this using like a microcontroller project, just because you can't have code that runs fast enough on a microcontroller to actually implement VGA. Because on a microcontroller, you're bounded by, I don't know, maybe like 1 megahertz. You can't do it at precision of like 25 megahertz. So this is one of the best ways to actually utilize FPGAs in like a hobby project or in your own projects. So yeah, very commonly, if you look online of like what other people have done with FPGAs, one of the biggest things is implementing VGA and doing something cool. So in the last lab of this class, we will actually all be implementing a video game using like the buttons on the thing, and you'll have to plug into VGA and it will be the VGA timer that you are using for this lab. So it's all a little bit cumulative. Yeah, so get excited for that. Yeah. Okay, yeah, any questions on VGA or any of this? That makes sense. Yeah. I think Vivado probably finished, yes. I wanted to quickly open up Vivado. Yeah, so you can open up, where is it? Yeah, so I'm going to now open up the Xilinx project that was generated. So here's the Xilinx project. I'm gonna copy relative path. I'll type in Vivado and open this. It'll take a second. While that's happening, I'm gonna pull up the next thing I want to talk about. Okay, it is opening. Sorry, just 1 second. I should have been doing this in parallel. That's okay. Okay, good. So here is Vivado, and I wanted to open the implemented design. What does, while this is pulling up, can someone give me a definition of synthesis again? You can also look back in your notes. What does synthesis mean in the Verilog flow? No? Yeah. Exactly, yeah. So it's taking, so synthesis is when you take Verilog that you've written yourself, so high-level Verilog, and converts it into a netlist, which is just low-level Verilog, yeah. And that is different from implementation. Implementation is Vivado's name for place and route. And so with place and route, it will determine, like after it's generated this netlist, it will determine where to put all the standard cells and things, including all the flip-flops, all the muxes, all the lookup tables, and also the RAMs. So so here we can see the implemented design. I wanted to highlight the clock signal because clock is pretty important because it connects to all the flip-flops, and it also connects to all the RAMs. So I've now selected this, and notice, so if I select each of these little signals, so we can see exactly where the wires are for them. So for example, so here is the H-sync wire. Can you see that? It's a little small, but you see how it's like highlighted white now? I can also, I can select the clock, and I can see where this is. And you can see it's like a really big wire, right? It's like all this white stuff right here. And that's because the clock is just spans all across the chip. It's called a global signal because it's spanning to every single one of our flip-flops. And I can float this window out to get like a better view of it and expand it. Yeah, and so here is all the clocks, and we can zoom in to like really see what it's connected to. So I'm zooming in. So here is like a big wire, and it's like fed into this, and okay, and do we have a guess for what this is? Yeah, so it actually looks like this is RAM B. What is this? Yeah, this is a RAM. So this is a memory that is inside of the FPGA. So it looks like, yeah, this is this big cell right here. I was hoping it was going to be a flip-flop, but actually it looks like it is a RAM. So yeah, so you can see that the clock signal is fed into this. And I think I accidentally deselected it. Let me quickly fix that. Cool. Good. Okay, yeah, so there we go. Okay, let's see if we can find a flip-flop, though. All right, it's got to be flip-flop. Oh, maybe these. Does that look right? Oh. No. Well, somewhere on here, I found one last time. Oh, it's this? This looks like a flip-flop. Haha, there we go. Okay. AFF. I don't know what the A means, but FF, flip-flop. Yeah, so there we go. So yeah, so we can actually, if you wanted to, you could look through this big implementation diagram and look at where all of the different flip-flops and all of the memories and things are generated. So after you've run your Verilog, you can go and see this. But your clock signal, you can see it's spanning all around. And your clock is often the most power-intensive thing in your whole design. Oftentimes, your clock tree can take up upwards of 20 to 30% of your entire power usage on your entire chip. Let's think about why for a second. So in CMOS, when does CMOS require power? Or when does CMOS take up the most power? Yeah. Exactly, yeah, so switching. So generally CMOS, like if it's stable, we can almost assume that it's taking up 0 power. But the second that it switches, the act of it charging up, or like charging up the wire that it's connected to, that is what takes the most power. So CMOS, yeah, switching is the thing that takes the most power, okay? Now let's imagine this clock signal, right, that's oscillating, goes from like 1 to 0, 1, 0. And when it switches to 1, how many like flip-flops are going to have their value changed? I mean, like potentially all of them. Like if your design has maybe like 100 flip-flops, it's kind of the worst case scenario. It's like now all of a sudden you have this huge spike in power because your clock is oscillating. It's oscillating. But every time it oscillates, when it shoots up to to 1 volt, now every single flip-flop, they all could charge up all at the same time. And so what you get is like just crazy power spikes whenever your clock goes high. So what you'll see, yeah, this big power spike, and then it'll kind of level off, and this big power spike, it'll level off, big power spike, level off. That's what would happen if you were to try running like an analog simulation, if you're like plugging this into like SPICE or something, trying to see exactly what the power and the resistance is and everything. Yeah, so it's kind of funny that we ended up designing chips this way. It's actually not the smartest like long-term solution of having every single thing in your chip all switch at exactly the same time. So anyways, just think about that. It does simplify things a lot. So in this class, that's all we're going to be thinking about. But there are ways of mitigating that and having like multiple clocks in your design. Yeah. Okay. Cool. And yeah. So speaking of having a circuit change flip-flops, I want to now go over. I want to hand draw a circuit, and let's try to analyze this together. Yeah. So now that we've seen this, let's go back to the iPad. Okay. So let's say we have flip-flop with D input, Q output, and let's say we have an inverter passed in. We have like this circuit right here. Okay. And let's say that this inverter maybe takes 1 nanosecond. Okay. If we have this circuit, then what is the fastest speed that our clock can change at in order to still make this a valid circuit? So we should imagine, right, so if it's inverting every cycle, so we should imagine like if this is our clock, right, so this is our clock. then our Q should kind of just be like slightly delayed from this. So let's say it starts at 1, and then after that, then it'll go down by 1, go up. So this is what potentially like Q could look like, right? Okay. So this is what we want. So what is the fastest clock frequency that now we can run at? All right. Anyone have an idea? Yeah.
1 gigahertz?
Yeah, exactly, 1 gigahertz, right? Because we have 1 nanosecond delay through this. So that means that, so if we're currently outputting a value, let's assume like, yeah, 0 delay through maybe this flip-flop through this wire. So it, the value comes out of this Q, comes in here, then it takes a full nanosecond to propagate through this inverter, then finally passes into D. And so therefore, the clock period, meaning the distance between these pause edges, so this distance right here must be at least long enough to account for all of the delays in the circuit. Yeah. Versus if we didn't have that, what would probably happen is we would there wouldn't be enough like time for it to for the data to propagate through, and so most likely you would have like just a flip-flop that's stuck at the previous value and it just wouldn't update. Yeah. So I'm going to say must be at least 1 nanosecond. Okay. Okay. So this is kind of a basic model, though. This isn't exactly correct, though, because there actually is going to be some delay that's introduced by this flip-flop. And there are a few different types of delays. I'm only going to talk about one for this quick example. But let's assume now we have maybe some delay after we've received the clock like pause edge. So if we receive a clock pause edge, it comes in here, and maybe there's some clock to Q delay. So clock to Q delay. And let's assume that maybe this is 2 nanoseconds. Okay. So if that is the case, then this this circuit is going to change a little, or sorry, this waveform is going to change a little bit. This Q, what is going to happen to this Q right here? Yeah, it's gonna shift over a little bit because now there's a little bit of delay, this clock to Q delay. So we had this pause edge, and so therefore it takes just a little bit more time. Yeah, and maybe this right here is 2 nanoseconds. So if this is 2 nanoseconds, then we also need to ensure that now this right here, so we can see that now our range is just a little bit shorter. Now we need to make sure that this is, whatever. Whatever. Now I've lost my train of thought, but yes, but now our frequency, our maximum frequency is now going to go lower. So let's assume that now we still have this 1 nanosecond delay in the inverter, and now we have a 2 nanosecond clock to Q. Okay, now what is the fastest frequency that this design can run at? Or what is the minimum period first that our clock can run at?
3 days.
Yeah, exactly, right, 3. So if our clock must be at least 3 nanoseconds, then what frequency is that? So we could probably just divide 1 gigahertz by 3, right? So what is 1/3 of a gigahertz? You need to shout it out.
333 megahertz.
Exactly, yeah. So 333 megahertz. Yeah. Okay. Cool. You know, this is good. There's actually other delay that now we need to think about. Okay, so now we have our clock to Q, but if you look here, so let's say that maybe this whole time right here, maybe it took the entire duration in order for the data to propagate fully through this inverter. So let's say like, okay, so right here is the earliest that the inverter can see that, okay, now we've started switching to 0. Okay, so now we've switched to 0, and so now the output should be 1 out of the inverter, but maybe it's like, it's still charging up, maybe, okay, starting like here, it's at like 0.1 volts, and then here it's at maybe like 0.5 volts, and then, okay, perfectly right here, now it raises all the way up to 1 volt. Well, now that kind of cuts short the D side of the flip-flop, we actually need to make sure that the data arrives just a little bit early, just to make sure that like now this flip-flop has enough time to charge up its internal transistors. So therefore, we can't just exactly right on the money have the inverter change at this point. So actually, we need to have the inverter like set up the D side of the flip-flop just a little bit earlier, and that is called the setup time. Okay, so oops. So I'll highlight clock to Q. So this is clock to Q, but the setup time now is how much time before the positive edge that D should be valid for. So this right here, this is setup time. So you can see, yeah, that there should be an amount of time that it is valid for before the pos edge. So setup time, so let's say this is maybe 3 nanoseconds. So now let's draw out this waveform now according to all these correct delays, and maybe let's do it at I don't know, maybe 100 megahertz, and see what that looks like. Okay, so we have our clock. And so we receive our first pos edge here. So we need to make sure that our D arrives before this pos edge. So I'm going to add a D signal to this waveform. Could we turn off there's something, yeah. Thank you. Okay, cool. So yeah, so D can come in, and D needs to be active, needs to be valid at least the setup time before. So the setup time we're saying is 3 nanoseconds. I don't know, maybe that looks about like 3 nanoseconds. So this time right here is 3, okay, and maybe it is set up as 0. Okay, and then after that, then we have this clock to Q delay, and so that means that now, so we receive this pos edge, and so now there is a 2 nanosecond delay right here before the Q actually changes from 1 volt now to 0 volts. Okay, and then after this, then now there is a little bit extra delay, right? So finally, so Q has gone down to 0, but then D doesn't immediately shift back up to 1 volt, right? How long does it take now for D to switch back up to 1 volt? So we have this inverter that is 1 nanosecond. So how long will it take?
4 nanoseconds.
Yeah, it'll take 1 nanosecond. So D will now take 1 nanosecond. And therefore, after this, then it will go high. And it'll stay high until right here. Okay. This making sense? Well, now we've received another pause edge. So I guess now the question is, well, did we satisfy the setup time? Like, did we arrive early enough? And well, our setup time is 3 nanoseconds. And I mean, just kind of eyeballing this kind of crude diagram that I drew. Yeah, actually, it does look like maybe this is at least 3 nanoseconds right here. Okay, so it repeats again. Okay, so now this right here takes 3 nanoseconds. And now there is a little bit of a delay before Q changes, right? This delay, how long of a delay is there before Q changes back up to 1? Yeah, it takes 2 nanoseconds after the pause edge. So we receive a pause edge and then 2 nanoseconds. Right there. Now it goes up. Okay. And then if we receive this now, then how long does it take for D to now change back down to 0 volts? Takes 1. Yeah. And now it will change. Okay. Yeah. It's gonna make sense? Yeah.
Sorry, can you like explain what the setup time is? That's like between the clock going like the positive clock edge and when the change actually occurs, or is that the clock?
Exactly. So setup time is the time that D must be valid before the pause edge in order for Q to work properly. So setup time is the time before the pause edge that D must be valid for. Setup time, and I'm gonna write that out. I'll just do it on this. Okay, so setup time.
So that's just like it's just like waiting and then
Time.
the pause edge goes up, it makes the change in Q.
Exactly. So it's the time before pause edge that D must be valid. Time before pause edge that D must be valid. Yeah, so we can see that D is in fact valid 3 nanoseconds before this clock pause edge. So therefore we're good. And so notice that like if I had drawn this out to a little bit better scale, it is just the minimum time. So we can see that like, so 3, like it just needed to arrive. Let me correct this actually. Slight mistake. Yeah, so we can see that, so here's the pause edge, and the pause edge is expecting that at least 3 nanoseconds before, D should be valid for all this. And we can see that D is in fact valid for this whole 3 nanosecond period. Not only that, but it was actually valid a little bit before that too. So it was valid for this whole period right here. But all we really cared about was just this time. So this is the setup time. Yeah, so it needed to be held constant for this entire duration before this. Yeah, and okay, yeah, makes sense. Yeah.
Well, so that's just like given to us, that's just we need to know that in our like diagram we need to have that 3 nanoseconds. It's not like why does it need that?
Exactly. Yeah. So every flip-flop cell. So depending on who makes the flip-flop, each flip-flop will have slightly different characteristics. Like the flip-flops at TSMC, the flip-flops in your Xilinx FPGA. Every flip-flop is different and will have different parameters. These are realistic, these are fair parameters for this teaching example. But yeah, so the setup time I'm just giving to you is just 3 nanoseconds here. Maybe this is TSMC's whatever 130 nanometer process or something. That's just what these numbers happen to be for this case. Could be that that they're completely different. Yeah. Sure. Yeah. Question.
Where are you reading the clock signal from on your diagram?
Reading the clock signal from?
Yeah, where is that coming from? Like on the diagram, which wire is that?
The clock is implied to be an input right here.
Okay.
I did not draw the clock because anytime that you ever see this symbol right here, it implies that there is a clock signal that is just kind of hidden from the schematic, but it is in the circuit. Yeah, it's just a way, this is a very common thing that people who draw schematics will do is, just hide out the clock signal. But you can imagine anytime that you ever have anything related to a flip-flop, you are going to have a clock associated with it, whether or not it's actually mentioned. There is a clock always whenever you have a flip-flop. Yeah, question.
What happens if before the process G isn't valid for the set time?
Say it again?
What happens if G isn't valid for the set time before it reaches the passage?
So you're saying what happens if, if maybe this inverter maybe took like 5 nanoseconds or something. So it took too long for D to become valid. Yeah, incredible question. So what happens, so let me redraw this slightly. Well, if maybe D now, was 0 for a little bit, and then, oh no, in the middle of the setup time, now changed something. This is called a setup time violation. Yeah, and this means that Q will actually probably not work. And what would happen is it would just probably stay at whatever its previous value was. And yeah. What was that?
So that is lost.
Yeah, exactly. So this, even though, if you zoom in, you can definitely tell it's like it was valid before the pause edge, but it wasn't valid far enough in advance of the pause edge. Yeah, so this 3 nanosecond setup time, it was expecting it to be 3 nanoseconds, valid 3 nanoseconds before, but it ended up not being valid for long enough. So therefore, Q didn't work. So I'll write that out. So setup violation. Okay. Yeah. So this is cool. I want to show you another characteristic of flip-flops. Things get a little bit confusing at this point. I'm going to try a different explanation than I've tried in previous quarters, so hopefully it'll be a little bit better now. But I've been lying to you just a little bit, because if you notice that, so I'm assuming that the setup time is like how far in advance of this flip-flop and how far in advance of this pause edge that it needs to be like held for. But actually, this is assuming that there's another characteristic called hold time, and this is assuming that the hold time is at 0 nanoseconds after the pause edge. So there's a characteristic called hold time, and what it states is how long after the pause edge you actually need to keep D steady for. Because if you think if you just let me draw it out. So if I, instead of so maybe I'm passing setup time now. So you can see my D is quite in advance. It looks good. But then I go and I extend this. Well, if I cut this off a little bit too short, like maybe I changed this a little too early. See that? So I didn't hold it all the way until 0 nanoseconds, like on the pause edge, the 0 nanoseconds after the pause edge. So since I changed D just a little bit too early, we would say that this fails hold time. So now this is a hold time violation. Hold violation, because I didn't hold the signal for long enough. Okay, makes sense, right? Because remember, so we need some amount of time for the D input to charge up. So we call that actually the timing aperture. So the timing aperture is how long your flip-flop will sample your D input before the pause edge. And if your D input is valid for that entire sampling aperture, timing aperture, then Q is valid. So we can see this red mark right here. This is denoting our timing aperture. And but since we have a hold time violation, Q did not properly change to 1. Instead, Q was just held at 0. Yeah. Good. And in fact, this timing aperture is different on every flip-flop type. So yeah, TSMCs, Global Foundries, like every flip-flop will be slightly different, have slightly different characteristics. And you may have timing apertures that are like very long, which is bad, right? Because this means that now it takes a very long time for our flip-flops to charge up. But you can also have flip-flops that have very short timing apertures. You can actually have them so that they are sampling maybe like in this region right here. So they actually are fine with you changing their value like right before the pause edge. You see that? So if you change the value like right before, it's still okay, because this is like the only window that it actually samples in. Let me pull up a website that I made that I think will better explain this. I think I put this in the resources tab. So this is a website that I created. So it's called the Flip-Flop Visualizer. And so here is our D input, here's our clock. And you can see these red bars right here. This is our timing aperture. So on the left side, this denotes our setup time, and on the right side, this denotes our hold time. And so notice that, yeah, occasionally you can have hold time that is actually like ends a little bit early. So it's really nice because that means we have really short timing aperture. So we're going to be like, it takes less time for your flip-flops to charge up. And yeah, and so I can slide this along, and you can see, so if I now, yeah, okay, so here you can see Q, and if I bring this in, we can see, even though I'm in the timing aperture, this sample is not being correctly reflected by Q. You can see there's still like a long delay. What violation would this be called right here? Yeah, this is setup time, right? Because I didn't set up D early enough. So if I now move it, there we go. So now I've set up D early enough, so now our value is correct. But yeah, if I bring it a little bit too close to that setup time, then, dang, so now I have setup time violation again. Okay, but yeah, if I now bring this over, but you can see, so this blue line, what do we think this blue line represents? This is the clock to Q delay. So if I go exactly down, you can see that this Q right here is actually perfectly in line with this blue line. And this blue line has a little bit of delay. So this is the clock to Q delay. So for the time for clock to go positive, for Q to actually change its value. So you can see, yeah, there's a little bit of delay. Similarly, so let me now show you something else that can happen. So let's say we wanted to, let's say that now we wanted to send a 1 into Q. And if I now bring this side just a little bit too close to this side of the timing aperture, then now it fails. So what is this violation called? This is a hold time violation. Yeah, because I'm just a little bit too close to the end of this. I need to extend this outside of this timing aperture, and then now it'll work. Yeah, and it goes for both falling edges and for rising edges of our flip flop. Okay. This makes sense. Good. That was a big information dump. This will be very helpful on your homework 3, because homework 3 is getting more in the weeds of flip-flops and their timings. Yeah, so good. Okay. Okay, I'm not going to do a participation question, but I will ask you a question that we will spend 1 minute thinking about, and then we will answer. The question is, if you were to write an equation to find the minimum clock period of a circuit with a flip-flop, what would this equation require? What delays would you have to add up to find the minimum clock period? Okay, I'll write that out. But yeah, please think about that, and then we will answer it in about 30 seconds. So. And then second question is, how do you convert from a clock period to a clock frequency? Okay, can someone shout out a delay that we would need to add together? So there's 3 things that we need to add together. So what is one thing that we would need to add? Setup time. Okay, what's another? Clock to cue. Yep, and then what's the last one? So not hold time, because hold time is just how long you need to hold it for before your circuit will break. If you don't hold it for long enough, everything will break. So it's not necessarily how fast your clock frequency runs at. What's the other delay? What was it? Exactly, yeah, so the combinational delay. Okay, and then how do you convert from a clock period to clock frequency? So we can say T denotes time, period, and then let's say F is frequency. So what is the equation? What is it? 1 over T, yeah, so F is equal to 1 over T, period, F equals 1 over T. Yeah, you will also have to do a lot of conversions from frequency to period, especially on your midterms and on your homework. So, okay, thank you so much, everyone. That is class over. Feel free to come up with any questions.